The next talk is Anna Retore, novel techniques for constructing and deforming integrable model. Please.
Thank you very much. First of all, thank you very much, the organizers, for inviting me. It's a great honor to be here today. Unfortunately, I've never met Rodney Baxter, but his work, of course, has a very strong influence on my own. It is a great honor to be here today. And I believe that his work has been influencing many different fields, from statistical mechanics to string theory and mathematics, like we see examples of his work. And more recently, we have seen like integrability appearing in various different contexts, like including quantum computing, systems that are in contact with an environment like Lindbladians. Like now we have this generalized Gibbs ensemble, for example, cellular automata. And of course, we have like integrability related to higher dimensions and even coming from like a Fordisher-Simons. So as a, like we all know, like the Young-Baxter is very important. And my talk is basically about how to construct more solutions of the Young-Baxter systematically. And this will be like with all these applications, we know, so if we know that the model is integrable, we know we can do so much with this model. It's a nice tool to have new tools to solve the Young-Baxter. So let me just start by making the distinction between, so if we see the Young-Baxter, we have sometimes like constant solutions, we have spectral parameter dependent solutions, and they can be of difference form. So when R of U comma V is R of U minus V, so you can write the R matrix as just depending on one parameter, but it can be also of non-difference form. And this last type is much harder to construct unless you know, unless you assume a certain symmetry or you know certain like quantum group symmetry that you expect. Like in general, this last type is very hard to construct. So how to know if a Hamiltonian is integrable, and when it is, how to construct the R. So of course, this like Baxter and a lot of people in here today, and for sure this list is not it's still incomplete. So a lot of people contributed to this problem, and in particular, there are various very like beautiful techniques. Baxterization, for example, you can use as we just heard to go from constant solutions of the Young-Baxter to spectral dependent ones. If we have quantum symmetries, quantum group symmetries, we can construct the R matrix that has that symmetry. We can use expand the R matrix. For example, for the case where the R matrix is regular, we could expand around like U equals to 0 and have like a series like this and try to solve order by order and find some pattern and resum. This was done in the literature. We can also, of course, try to directly solve the Young-Baxter, which is quite hard, but like by, for example, applying a derivative with respect to U, and then sending V to U, and then solving these PDEs, we could do that, but this is particularly hard for non-difference form. There were cases also like people classified which kind of, so actually now if you think about the Hamiltonian instead of the R matrix, let's think about the Hamiltonian. In terms of knowing if the Hamiltonian is integrable, like there were like people classified integrable mod, like which models are solvable by coordinate Bethe-Ansatz for certain cases. We have, of course, the Rashetikian condition, and if we plug here a certain Hamiltonian, if we can find an A that satisfies this equation, it's a great, like it's a very strong indication that our model is integrable. And we have also, like in the integrability test, that I believe was mentioned by Balázs yesterday, where if you have a Q3 written like this, you can check that if this K, this charge commutes with the Hamiltonian, your model is probably integrable as well. So these are all like beautiful ways to attack this problem. But I would like to ask, like, if you would like to go beyond quantum groups, if you'd like to investigate, just take a matrix and investigate for which choice of like the functions on this matrix, this Hamiltonian, this density Hamiltonian, just a matrix, for which choices of these functions is this Hamiltonian integrable, or if we want to find new solutions of the Young-Baxter of non-difference form systematically, or not necessarily of non-difference form, but without assuming that it is difference form. How do we do that? So with Marius, Chiara, Anton, and Paul, when we were all in Dublin, we developed this method we called the boost method, because it's based on this boost, the so-called boost operator, where you can do this systematically. So first of all, we need to say what are our boundary conditions, so for which cases we can actually apply the method. So this works for regular R matrices. So if I take an R matrix of U comma V and I send V to U, I expect that this will reduce to the permutation operator. And we want the derivatives of the R gives us a Hamiltonian. But if the model is of non-difference form and we do define this like in this way, you see that the density Hamiltonian depends on U. So one of the spectral parameters is still there. Well, so for this talk, a very important object will be the boost operator. So for this discussion here, you can get this Q3 by a boost operator, as Mathieu and Grabowski showed. But that is for difference form models. So almost 20 years after, John Links and collaborators introduced a boost operator that works for non-difference form. And then we thought in using a mix of what Mathieu and Grabowski did, using the boost operator for non-difference form, and mix this with the Sutherland equation. I will show you soon how we did it. But so this operator, sometimes also called the ladder operator, so has this extra derivative term. If this derivative is not here, we go back to the difference form case. And why do we like this operator? It basically gives us higher charges by commuting with a smaller one. So if we start with Q2 and we commute with this boost, we get Q3. And in particular, Q3 looks like this. So it's exactly the formula from before, but with an extra derivative term. You see that if it was difference form, this Hamiltonian will be constant and this term will be 0. Okay, so we have all the ingredients. So let's say what the method does. So we start with a very traditional step. Basically, we start with the Young-Baxter and we apply a derivative with respect to one of the parameters, let's say U, and we send V to U. And then we use those boundary conditions I told you at the beginning, the regularity, and that the derivative of the R gives you the Hamiltonian. We plug here and we have a type of Sutherland equation. But this is still very hard to solve because we don't know the R, we don't know the H. So even if it's quite complicated in general. But what if we could obtain extra information about this Hamiltonian using the boost operator? Like using some external thing, like, so the boost operator can give us information about this Hamiltonian in the following way. So let's start with an example. I took a very simple one. This model is very new, very known, sorry, not new at all. It's very known, as you'll see soon. It's just a very simple case, so I can show you. Okay, so we start with this density Hamiltonian with some functions that we don't know what they are. We use the boost operator to compute Q3. And then you see that Q3 would have like quadratic terms on these A's and linear but derivative terms on them as well. So if you write the density of the third charge, it looks a bit like it looks exactly like this for this model. Okay, so we now ask that Q2 and Q3 commute among themselves, and we solve the ODEs carefully. In this case, you don't need to be very careful because it's very simple. and you just basically get A3 and A4 in terms of A1 and A2. So we have here a density Hamiltonian that commutes with Q3. So we check it that the first two charges commute. So we are calling it potentially integrable because we don't know if it's fully integrable yet, but it satisfies the first condition. So now we can go back and plug this in the Sutherland equation and solve these PDEs for R. And what we obtain is this. It looks a bit ugly, but it's like just a 6-vertex model. And it's actually XXZ in disguise. So just to recap, the method, the idea is you start with a density Hamiltonian. It could be very complicated. It could be higher rank, like in acting on higher Hilbert spaces. I just showed a very simple example to show how it works. So you start with these ansatz for the density Hamiltonian. You construct Q3 using the boost operator. You compute Q2 with Q3 and solve the ODEs. So if it was a larger Hilbert space, like a model in a larger Hilbert space, you have as more non-zero elements you start with, like more solutions you have usually. So you end up with several potentially integrable Hamiltonians, density Hamiltonians. And then we plug each of them in the Sutherland equation and solve for the R matrix. And then we check Yang-Baxter. So we have been, like for all the cases we applied the method so far, Q2 with Q3 was enough. It basically fixed completely for us what density Hamiltonian could be. We always found an R without having to put extra conditions on this. So this is already a conjecture from like related to the ratio taking condition. There was a recent paper by Akihiro Hokio where he says he has a proof, which I'm very interested to understand how he did it. I still didn't manage to read it, but so maybe we have like an explanation for this conjecture, which would be nice. But what we expected when we started the method was that we'll find some interesting solutions, probably most of them, depending on the initial ones, that's most of them known, perhaps a few new ones, some trivial ones maybe. But what we actually found were like a lot of dependent solutions. So it's basically a mess. So if we start, we just blindly apply everything. It's very confusing because you get a lot of solutions that are not independent from each other. And then it's a lot of work to put them, separate them and say which ones are in each equivalence class or something like that. But the cause of this is also the solution for the problem, which is there are many transformations you can apply in their matrix that preserve Yang-Baxter. So if you change normalization, you could reparameterize the spectral parameters. For non-difference form, you can change U and V to f of U and f of V, like any function. It still satisfies Yang-Baxter. You can do basis transformations, discrete transformations like permutation or transposition and twists. And all these preserve Yang-Baxter. So what we can do is actually use these to, from the beginning, fix certain positions in our matrix to 1 or 0. And this reduces a lot, like from the beginning, like if you do this, you can do strategically as well. You can look your system and see which choice will actually help you to solve the system and make that choice. You just have to be careful because it's not every element you can put to 0 in this kind of thing, but it depends if it's diagonal or not, and like you have to be a bit careful, but there is a lot you can do by starting like this. So this disadvantage becomes an advantage. Okay, so we apply this method for various setups. And one of them was like we classified SU2 plus SU2 systems, both of non-difference and difference form. And then we found the expected models like Hubbard model, uh, uh, SU4. Like we found all the expected models on this class, but we also found some new ones. So if you just ask for to have SU2 plus SU2, your Hamiltonian look like this. The density Hamiltonian looks like this, where the phi's are the bosons. So you phi1 is a site with no particle. Phi2 is a state with one particle spin up and one down. And then the psi's are the fermions. So you have 10 parameters. You can solve the system using our method. You can and you find three of the solutions you find are very peculiar. So they are such that when the density Hamiltonian acts on a state that is a boson times a fermion, like a boson a fermion, or the other way around, it gives 0. So these are highly degenerated. These 3 models are highly degenerated. This A, B, C, D is like these letters. The expression for them changes from each of the 3 models. There are 3 different models. So this, but the 3 of them have this feature. So it's basically the particles only moving the chain when they are not alone. So if they are in pairs, then they can move. But if a particle is alone, it just stay there. Uh, and if you compute, for example, the periodic spin chain for 4 sides for these 3 models, you get these are the degeneracies you find. So the models look very different from each other. Actually, 2 of them are Hermitian and 1 is not. Um, but they look to have a lot of symmetry in addition to SU2 plus SU2. So one problem I'm still very interested in is trying to understand what are these models. We failed to map them to anything in the literature so far. So uh, if you have any, so if these degeneracies look familiar to you, please let me know. Um, but so far we failed and it looks new, but it's very hard to check because all these transformations I mentioned can be applied in very different orders. So the comparison with the literature is actually one of the longest parts of the project. Okay, but this model I just showed you is actually of difference form, these 3 models. And actually the strong point of the method is non-difference form. Like we can it's systematic and it's not very difficult. Like it gets, of course, very difficult if you put all the elements in your matrix non-zero, but you have a lot of control, so it's quite nice. At the same time, these are like non-difference form models. The ones we know are very interesting, like the Hubbard model. There are some free fermion models. Models in the context of ADS-CFT are of this type, but they're very hard to find unless you are using some quantum groups to find them. That was what was done in this case, for example. Just like brute force or like trying to solve Yang-Bax is usually quite hard, but our method can do that. So we thought, why can we try to use these to deform one of these models in ADS-CFT? And there is a very, ADS3 is a very interesting one. So the S matrix, so if you're not familiar, like what you need to know for this talk is like this S matrix uh, uh, that describes ADS3 times S3 times D4, has the following properties. It has factorization, so the full S matrix can be factorized in two smaller ones. It has block structure, so each of these smaller ones can be written in block, and this is schematically, if you, but it can basically be written like this. And more interesting, the full S matrix satisfies Yang-Baxter, the small ones, and these little blocks also satisfy Yang-Baxter, these diagonal ones. And the off-diagonal ones, they are like a lax. They satisfy like an RLL with the diagonal ones. So there is a lot of integrability here. So this model is like quantum, like the full quantum S matrix is known. It satisfies Yang-Baxter. And these little blocks are basically 4x4 blocks. And the undeformed one behaves a bit like XXX, but of no difference form. The the Q-deformed one, so there is a Q-deformation of what I just mentioned. It has exactly the same three properties, and it behaves a bit like XXZ. So our question was, can we use our method to find all these blocks such that this is an elliptic deformation now, but these three properties are still satisfied. We applied the method with Marius, Anton, Chiara, and Paul in Dublin. And we found, and something I forgot to say is that these off-diagonal blocks are not regular. So we need to use the method together with some tricks to find everything. Because these two are not, don't reduce the permutation when you put V equals to U. So the diagonal part, one of them is given by this. So you have these Jacobi functions. You have a bunch of functions here, this F and G can be completely general as an integrable model. They, of course, have to have a very specific form when you, if you want to reduce to ADS 3 or like to interpret it as a deformation, but in general, these are general. And then these are the left-right blocks. Also, you have some functions, but now there are two different ones here. And then you have the other two blocks that I didn't write. And we were forced to put the modulus of the Jacobi functions the same on both the left and right blocks. But yeah, so we were able to construct these. And it's quite, it reduces to ADS 3 in a certain limit. And actually, yeah. But then our next question was, does this make sense as a sigma model? Is there an integrable sigma model that gives us this, that if we would be able to like compute it 3 level and then quantize, would give us this model? Or it's just a coincidence, like we can find a matrix that we can embed inside another one and like in a certain limit it works. So we started investigating this question with Fiona Seibel and Ben War in 2023. And what we tried was basically the easiest way in this case, basically the only way we know is basically deform the PCM. This is the group you need to use, is SL2R times SU2. And what you do is basically you take this action and for the undeformed case, this will be basically 1, like an identity in the middle. But if you want to deform it, you put an object in the middle. And basically, we are asking that this object, when acting on generators of the SL2R algebra, give again the generators with these coefficients. And the same for the SU2 part. But we are asking these coefficients, if you want elliptic, we are asking them all to be different. If we do only 2 of them to be different or all of them the same, we reduce to the undeformed or trigonometric case that are known. So we knew this works for the Q deformation. So we tried the same for the elliptic. And yeah, so this G that you had here is an element of this group. And these are the coordinates in the worksheet. If you like, these are the coordinates in the the target space coordinates. These are in the ADS part, and these are in the sphere. And for now, we are only doing bosonic. So if you are a bit familiar with string theory, you can compare with the Green-Schwarz action. You find this B field, but you find this metric. So you have a metric that's very ugly because you have all these parameters. But it's fine because it's a bit unconventional if you're used to the topic, the way we wrote it. But it was because if we did in the standard way, we didn't have the right isometries, because we need now to fix the light cone gauge to be able to try to quantize the model. And we need 2 isometries. And by doing this way, if you see, phi and t only appear in the derivative. It never appears alone inside of a sine or a cosine or anything. So we needed this, and this was only possible by doing a bit this kind of rotated choice for this G. That's very unusual in a way. So we fix light cone gauge. And then we can compute the scattering matrix. So it just expand and then you compute perturbatively order by order, like Feynman diagrams, basically. Using these, so the dispersion relations are horrible. It's like these, and these gammas are functions of alphas and betas. But we can compute the three-levels matrix, and we found that satisfies the classical Yang-Baxter. So we are happy. But we only put the bosons, and then we thought, let's try to just bootstrap the fermions, like do a very silly computation. We put the elements that where the fermions should be in the matrix, and we tried to see if there was a solution of the classical Yang-Baxter, if we could fix those elements to give the classical Yang-Baxter. And if we assume factorization and block structure, it was impossible to do that. Yeah, so having all the three things that we had before simultaneously seemed impossible. So this is already a good indication that the model that we found by this elliptic deformation of string sigma model is not the one we found before. But a few weeks ago, Ben and Fiona put the fermions and compute explicitly the S matrix, and they discovered which of the three actually fails. And it's the factorization, like the big matrix is now not two small ones. You still have some kind of block structure, but the factorization is broken. So this, yeah, for sure is not the model we found. It doesn't mean our model doesn't come from a string sigma model. It just means that it doesn't come from deforming the string sigma model in the way we did it. But the challenge now is like, it's a challenge for the method I just explained you before, because now we have this big matrix that is big blocks. Since it's not factorized anymore, like now you have these very big blocks, and this is not included in the classification we did before. So we can try to apply the method. So something I've been discussing with Fiona Seibel now is like, can we use our method, the boost method, to construct the full quantum S matrix? Because what usually people do is starting with the undeformed case, or with the, sorry, it's starting with the tree level they computed with from sigma models. They assume the symmetries lift, so they use basically quantum group symmetries to bootstrap the full S matrix, quantum S matrix. But this model is elliptic, so it's very hard to do that. It's much easier, we think, to solve our method directly and find and try to find what's the most general. Yeah. Sorry?
You're back.
I disappeared?
No, it's there. There was just a glitch
A glitch.
in space-time.
Yeah, so the last things I said is that you can use our method. So our plan now is using our method to find what is this. This that was computed using sigma model is not the one we expected before, but it's a larger matrix, but we can now apply our method again and try to find the full quantum S matrix by using that. So I have been telling you about this method, and we and other people already applied it for a bunch of setups. For example, we fully classified SU2 plus SU2 models, 15 more vertex model of non-difference form. So now a full 4x4 non-difference form classification is done. We also found some flag models, like some models that have some kind of flag manifold structure. It was used to find the first systematic classification of integrable Lindbladians and to find the DS3 and DS2 integrable deformations. So it has been working very well for all these cases. All the models we were aware they existed, we checked and they were included in the classification. And we found some extra ones that we were so far unable to find in the literature. So for now, we think they are new. But we are always happy to hear if you have any comment on any of them. Okay, so I presented you an efficient method to construct solutions of the Yang-Baxter equation, especially for non-difference form. And now we can use it for other setups. And in particular, I'm very interested in understanding in constructing the full quantum S matrix for this sigma model I showed you. But also still to figure out that other one, if it comes from a different elliptic deformation of sigma model that we don't know yet how to construct. Thank you very much for your attention.
Any questions? So I have a question. So you showed us the formula for 4x4 R matrix, 8 vertex model, R1, R2, 8. Do you find any new solution of this form?
So
This one, yes.
So first, yeah, this is like we were unable to map to anything in the literature, but this is more like a lax because it's the left right. So
No,
this one,
solutions which I know, symmetric 8 vertex model, which is a Baxter solution,
a
and
Baxter solution, yeah.
is a free fermion model with only one condition, only one quadratic condition on 8 coefficient.
Yeah, so I believe this one
Yes.
can be mapped to that one because there is no way around, basically, as exactly what as you said.
Okay.
But by applying lots of transformations on it, we could make it like, especially like we could make it relatable with ADS basically. So we solve it from scratch to find this, and we don't it with elliptic functions was quite hard to map one to the other. But but it has to be like we believe this one has to be the Baxter model for 8 vertex, the free fermion one. It exactly has free fermion condition, and when you compare with all this ADS story, actually all the models related to ADS3, ADS2, and deformations for all integrable, all of them have free fermion solutions. Actually, a free fermion condition actually satisfy the free fermion actually. Sorry, I don't know if did I reply your question?
Yes.
Okay, good.
Okay, any more questions? Let's thank the speaker again.